So I'm going to do a very light sort of guided tour of what we are with Boston and what we're doing, especially with the financial services industry. But I think I'd like to start with telling you a bit about my background. So I'm a computational scientist by background. I'm a software engineer. I used to develop computer languages. I was a core developer. And when I graduated, I worked in research and development on 4GL. So if anyone knows what fourth generation languages are, I have quite an appreciation of this type of tech, well, very much so. And when I graduated, I eventually went into the financial services industry by fluke. I ended up in a company called Salomon Brothers, and I worked on the arbitrage desks because they needed someone to do payoff formula for simulation models. And that was literally for the arbitrage desk in the early 90s with Myron Scholes as the head trader. Interesting character. And they basically trained me as a quant developer, so a quantitative computational scientist. And we wrote risk management systems for them for their fixed income and exotics for the arbitrage area. After working there, I then worked in JP Morgan for the Capital project, and I was actually involved, I'm still a member of ISDA actually, I was involved in the standards for FPML, and it's just nice to see how it's evolved over this time, and using this type of technology is absolutely brilliant. And Merrill Lynch wrote large-scale distributed computer systems for the risk management on there, using FPML at the end. You got swaps wire and all that kind of stuff out the back of it. But I was largely on the front office doing structured products, and then a few other banks. But I ended up in a hedge fund in Bluecrest, where I was doing the credit derivative side of it. It was getting more and more complicated, and Swiss Re. So I was working as admin in a hedge fund for that for about nearly 10 years, and I was dealing with all the software globally for it. And I looked after the back office very temporarily when my friend went slightly crazy for 4 months. But and I got a full appreciation of the sheer complexity of doing these things, getting everything right. And then ultimately, Deutsche Bank, I was one of the heads of platform engineering for Deutsche Bank in market risk with stress scenarios. Again, the stress scenarios you've got there, I totally get that. It's quite tricky. I was on with the modeling side of it, and then joined Boston as their technologist. So that's basically a little bit of a potted history. I've been in banking for 30 years, and it's a real pleasure. It's one of my first conversations I've actually had with people in the industry. So hello. Right. So about Boston. It's been around for about 30 years. They claim to be the first company to put a GPU in a data center. And my boss, Dev Tyagi and Manoj Tyagi, that own the company, have always, Dev's always complained at length how the fact that he wasn't the man to patent that, which he didn't, and the rest is history. But we had our 30-year celebration. We have a global presence, and we work with we're an elite partner of NVIDIA and partner with WSD. Thanks for having us here, by the way. That's really nice. And we actually resell globally, and I'm coming into working on the software side. So yeah, we distribute components. We build systems on a large scale for banks and for AI companies, ranging from we're kind of a broad church of different things. And we are heavily into AI, and that's one of the reasons I was taken on. And this is our global presence. We're nearly 400 employees in the main Boston company. We've got a whole series of partners which I'm heavily involved with incubation, and I'll come to that a little bit later. It's quite a large foothold. We've got quite a big presence in India, where we have centres of excellence, and we are involved with people in academia who are actually getting their PhDs in artificial intelligence and quantum technologies, and we're actually using them with our partners as well. So we're actively involved with education in that space. So there you go. And our alliances, clearly, WSD, but we're with NVIDIA, very, very heavily involved with NVIDIA, and we sell all kinds of hardware. I'm particularly interested in the computer science side, so I'm using technologies like GraphCore, which do what's called graph execution engines, which are really good for simulation models, if you get the precision right. Deterministic, this totally deterministic. And Boston's DNA is super micro. Now the reason I joined Boston is because there's only two types of machines that I never was kept awake at night. One was a good old Sun Microsystems, if you remember the Sun Microsystems. Wonderful. In fact, when I went back to Bank of America, actually, they still had my machine there. And we named them after vegetables. My machine was called Cabbage, which is, for want of a better word. So Cabbage was still there, and it was still working with the same power supply. doing the same experiments. Not that fast, but I quite like that. I like the Solaris. And Supermicro was the other one in Bluecrest. They can run on the edge, and they're very, very well made. And for me, joining Boston was a bit like, joining Bugatti. I wanted to go from being on the banking to having gone with the vendors because I thought it might be more fun. Answer, been there 4 years now, yes, it's much more fun. Okay, so high performance computing, you all know about this, you're all over this. We're using supercomputers, we're solving complex and data intensive problems in a massive scale, but we're using a mix of different types of compute now. In the old days, it used to be lots of CPU-bound stuff, and I had to constantly engineer the software to work 24 hours, make sure it's creating consistent numbers, so we do the regulatory reporting and all that kind of stuff, so it's utterly reliable. The model stability is a big thing I was involved in as well, model validation, which is extremely hard, especially with the regulators with their models, and then you have to cross-compare and so on and so forth. Even then, it was a challenge. Though generally you had to basically get the model validators happy, and you would tend to be okay. I did lots and lots of structured products and fixed income derivatives, by the way, for risk management. But we're looking in terms of HPC, and there's our circle of coverage for CPUs and GPUs. GPUs are now in the mix. We have a core of how a trade would be modeled in different ways, which you would represent in XML for trade sheets. You have a trade representation, you have the concept of a party or counterparty, you have a portfolio with a collection of trades, market data, which has many, many different meanings, and a model, which you generally work with. So generally they're the core ones when you write these risk management systems. And I've written for Swiss Re, I've written for JP Morgan and Merrill's. It's basically quite a simple principle. But you use more than one component, basically, at any one time, the interaction of them. So if you want to value something, you have a trade, you have the market data, you have the model, and you apply something to it to get your valuation. So these things are totally deterministic, and obviously with the likes of, well, actually CCAR was the most recent one, where you've got an FRTB, where you've got a massive computing to work on that particular space. You need to start thinking of how this can be done with other types of complementary technology. So the purpose of this is we're talking about heterogeneous compute, something which I very, very strongly believe in. But ultimately, this is totally deterministic, and all this type of reporting which you would have to the regulators and the counterparties, you know everything about that stuff, so I won't go into any more detail in that space. So, let's talk about artificial intelligence. A much abused term, to be brutally honest. A lot of it would be business informatics that people use, and the other parts of it are to do with more like a black box, so you're actually using something, you're training it. Different disciplines, but it starts from a statistical kind of discipline, and some of this largely would be used as an assistive technology, particular things, when you're finding anomalies, all that kind of stuff. But really you want that client to have an informed decision quicker than you doing it yourself and make less mistakes, which is what you want. Also, if you can go and find that information quicker, which pretty much Melody's doing, it's going to save an awful lot of time to get you close to the point where you can make the decision. And that's really absolutely critical to how this would work. So when we start thinking of AI and how it would apply, we start, our coverage gets a little bit smaller. So model valuation I found very, very useful actually. And I've been working with what's called quantum entropy sources. So when you go and do a simulation model, you can actually change it for something quantum, and it'll help you do your simulations more efficiently. So when you want to create new types of stress tests, new types of scenarios, it can help you with that in your models. And scenario risk is something which I was involved with at Deutsche. I was involved with I was actually responsible for that with a guy called Chris Scott Condit, and we worked on that in the scenario and market risk end of the world. So scenario risk is where I've basically come from, really. So with market risk, you might want to use bits of AI to work out new types of catastrophe scenarios and stuff like that. You might want to use that, but you'll still need to validate yourself. But you can't really, with some exceptions, you can't just generate a trade report normally, unless it's really, really clear, which would be a pass muster for a regulator, but maybe that's changing now, I don't know. Default risk is particularly interesting when you start looking at risk factors. And what is the new piece, because when it becomes to the risk managers, especially in a hedge fund, the chief risk managers, it's extremely important to the company owner to understand the nature of the risk that they're actually taking. So AI, pretty useful for that area. We've got fraud detection for emails, looking for changes in people's behaviours if they were being infiltrated in some way. So if they were being interfered with in some particular kind of sense, then they can actually go and report it, alert someone to say there's some anomaly happening here. Because in the new anti-money laundering rules, we especially had that in MLR rules in Deutsche, for instance, it was absolutely critical, and then you're responsible for it. But how do you search a sea of emails? How do you do it? You need some form of automation to help you work out where the automations are. In terms of cybercrime, Bank of America was quite an interesting one, because outside of Bank of America, people think Bank of America is the Bank of America. So the security department, the cybersecurity department, is absolutely massive. They get billions of hits at a time, because people think if they break Bank of America, they'll break America, which is actually quite amusing. Yeah, I had a conversation with a guy, I was sort of chatting with him, and he was just sort of explaining it. And he was getting alerts and stuff like that, and they managed on top of it. But actually, if you can preempt and find out where the anomalous behaviour is happening, you can kind of stop these things, and then you learn from it, and then it becomes part of another piece of AI, which I'm actually working on as a project. So basically, it'll kind of suggest anomalies for you to work, and it'll put them as its new rule base, and then you fold that back into your logic. Quite exciting, really. Anyway, so there you go. There's a sort of the kind of areas we talk about here. Counterparty risk, which you all know about. There's the risk and your counterparty. These are what they're called, well, it's been a while, but they're called bilateral security models. It used to be who's going to go bust when you're doing business with them, and it's changed to these models where you or the counterparty could come into a problem. And we've actually had that with in Greece. I don't know if you remember Greece bonds, and they changed the meaning of a default, and you had to do new rules for the credit derivatives standards and documentation. So I was involved with that in Bluecrest, actually. A challenge. So, rather abruptly jump to quantum. So, we're harnessing quantum mechanics. We want exponentially faster processing, and we want stuff which you can't do with a classical computer easily, right? And I'm actually with a team, with our partner company, actually literally now we've got our own chips and stuff, where we are actually using quantum technologies for finance calculations or finance kind of problems. It can actually be done. I've seen it. I was actually a bit doubtful about 6 or 7 months ago, but this is cutting edge kind of stuff, and people are buying machines like D-Wave, like, you know, it's probably well publicized. I don't know if it's Deutsche or Morgan Stanley or one of the big banks, and they are actually doing it. Unless there's someone from there could tell us. No? Okay. Okay. So now the universe shrinks, but in a very interesting way with quantum. So we had everything. We shrink it down a little bit more, and now we reach the point with the AI, we start talking about quantum to help you do your valuations. So I've been working with some Markov models, if people are into, I don't know how technical you are, so I won't go too much into it. But certain types of models benefit from an improved, what's called spatiality of the calculation. So if you're doing some simulation models, I've found an improvement, which I can measure repeatedly, which I've been quite surprised about. But I think in banks, everyone wants a 300% improvement or a 500% improvement. This is more marginal, but it definitely makes a difference. And then when you start talking about the actual modeling itself, to help you define the models, it's very good at finding parameters. It's called hyperparameter. You can actually use quantum. It's very good at vision recognition. So and things like that, and classifications, which you can do. We actually do now. I've actually got a demonstration if anyone's interested of it being done. It's a bit technical though, because it's all hyperdimensional stuff. But basically, 2 qubits can actually go and organize blobs of data much faster than you'd ever do with any form of hardware. And if you've got classical hardware, and if you were to scale it up, absolutely impossible to do it. And then obviously market data modeling, one thing is finding noise and nonlinear things in noise. So there's lots of stuff, especially when you start talking about algorithmic trading, for instance, and you've got high-speed data sources. They can be a little bit hard to filter and work out whether you've got blips and things going wrong. I mean, I remember back in the day with bond prices, somebody types in the bond price wrong, and you need to work out whether actually it is a move in the market or it's an error. And sometimes when you see the error, it can have a ripple effect on the market. So how do you know what's what kind of thing? So these are quite good at helping to identify those type of stuff. And obviously scenario risk, it can help, again, search a space where there's lots of different possibilities of parameters to suggest things to someone who's actually defining scenario risk models. So it's quite good for a risk manager, model validator, and so on and so forth. But again, these are assistive. You're not generating a trade report off of quantum technology. It's too far in the future, that kind of stuff for it. And by very nature, it's not deterministic, which is why I find simulation models quite interesting, because it's kind of not deterministic, but you end up with a repeatable deterministic result that's used to do your postings. And that's very, very heavily regulated. So you can't just throw this into the mix easily for everything. So in financial services industry, and I've been building some of these actually, pricing and risk modeling. So for pricing and risk modeling, you can basically change the random number itself. And I've found some differences with that particular kind of stuff. Now the big heavy one at the moment is portfolio optimization. You want to minimize the cost of your hedge, or you want to be on the buy side, sell side, and look at the factors in there. You can actually use it to help you manage a portfolio. And I'm actually building libraries now. It's actually actively being used, so you can help with optimal hedging strategies on, say, a derivatives portfolio if you're delta hedging. It actually has a practical use. I've built that. I'll come to that a bit later on. Third one's quite interesting, and we're actually doing some research on that. One of our partners is actually sponsored with NATO Diana project, and we're doing research in quantum artificial general intelligence. And in fact, I've just got a phone call from this afternoon, because we've actually built our own hardware as well, and it works at room temperature using photonics. But I'll save that for another discussion if anyone's interested. But that one is to do with equilibrium, finding an equilibrium of something. And so mathematical view will know about Ising or Ising machines. I think you say Ising. But by the way, you're looking for an equilibrium, and it's the same as a problem called the traveling salesman problem, where a salesman wants to travel from one location to another, and then to another and another and another, and use as little fuel as possible. There's a certain point where you just cannot do with a classical computer, and a quantum annealing machine does it for breakfast. It's easy, and that's definitely being used at the moment to use D-Wave. I think JP Morgan's using that at the moment, or Morgan Stanley. I can't remember which, and they use that to help suggest optimal portfolio strategies for traders for it. So you want to book as few trades as possible at as low a cost as possible, or maybe the cost of a trade, the cost of carry, will be quite high. You want to trade in all these different factors. It's very good at looking around in these kind of multi-spatial types of problems. And I can tell you from first-hand experience, I've had to write portfolio optimization stuff as a computer scientist in a bank, in fact in Salomons, to try and optimize whether you buy swaps, caps, floors, futures, and so on and so forth to hedge a derivatives portfolio for delta hedging, and it is a non-trivial exercise. It reaches a point when you've got so many products, you just can't do it. You have to make a decent guess, you have to start cutting corners. This actually does it for you properly, which is quite an interesting way of looking at the universe. And then the technologies, use cases, as I was saying, stochastic, that's your randoms, derivatives pricing, risk analysis. I've been doing some stuff what's called Hamiltonian Markov chain Monte Carlos, but basically tree prices. And then portfolio optimizations, as you know, hedging, swap netting, optimal arbitrage, which is a much abused term, arbitrage. I haven't worked in arbitrage. It's not quite what it used to be. It's intelligent proprietary trading in my view, but there you go. And credit scoring, so credit risk. Now, credit scoring is quite interesting because the models are still evolving quite a lot on that space. And like I said, in machine learning, we're actually using it in machine learning. So we're actually working on a project now, literally at this moment, that we can use it for large language models, and actually using it. In fact, I forgot to actually load the model up before I came here, but we're going to be using llama symbols, and we're going to be using it in a little use case with a finely tuned one, so then we can optimize that with a quantum technology. And there's some good reasons for that. We want to obviously get the results quicker. We want to keep that bottom line, the cost down, and it's in less time, because inherently it's a different type of computation. It's a non-classical. A lot of these you just can't do in classical at all. Well, so a lot of it you can, and using less energy. Now with a photonics quantum, proper photonics quantum, it's using 1/4 millionth of the power. So you have an A100 or an equivalent card. I shouldn't have said A100 because it's in video here. But you can do visual processing, and instead of using 200 watts, 300 watts, you use 2 milliwatts. It's another level of efficiency, because it's just using light at room temperature. It's entangling photons instead of electrons. So you don't have to cool everything down, And also you can use it for generating true random numbers, which is what these guys have done today. That's literally sat on a bench, nice and warm, creating perfect random numbers, which are very, very useful mathematically. And the scalability. Now, people always said, oh, I've got 1 qubit, I've got 2 qubits, I've got 3 qubits. There are ways with quantum computers that you can kind of chain them, which I never knew about until about 6 months ago, to be brutally honest, because they're educating me. A multidisciplinarian type of universe, because you need a theoretical physicist, you need a computational scientist, you need someone who knows how to do the business and try and get the message across, and so on and so forth. And we've got that combination, which is why I get pulled into these things every so often. I'm a computational scientist on there. We've actually got dedicated people doing quantum algorithms as well. So if somebody wants to try out an algorithm in quantum, we can do it. So, to summarize, we're going to heterogeneous computing. Before was using CPUs, now we're throwing AI into the mix, now we can throw quantum into the mix as well. So it's just a set of tools to help you make your informed decisions. And we're involved with every piece of that. I mean, Boston's history is mainly in the HPC background, but they know that they need to get involved in this space because it's much more, well, I think it's more interesting personally, but I'm biased. But the thing is, it's actually something which actually add value, on the bottom line, which would be, quite important on there. And it's very hard to find people with the skills. I'll tell you now, trying to recruit people to quantum algorithm writers, we've actually got them now. And we have technicians, such as myself and the teams that we've got to do these things. I actually have quantum hardware in our data center in 6TeRa in Reading. We've got 3 cold quantum computers with one of our partners, 6TeRa. And also we've got photonic, which I'm doing some other stuff with that. So I use quantum random number stuff. And this company, Sakai, that we're partnered with, is actually making their own in-house hardware in the UK, because we want to use them for many purposes, including military. So I can't go into details there. So the idea is it's adding more tools to help you do your compute efficiently and quick. And that's really what we're trying to do. We're trying to converge the best in class. So we have a quantum simulator. I built one recently, and it works. I've been using it for image classifications and it's quite pretty. So if anyone's interested, I'll send you a little video of it. It's quite exciting because I didn't know it was possible until I tried it. But I did have someone who'd done their PhD in what's called kernel trick quantum, really complicated, and then showed me. I thought, oh, pretty pictures. This is really good. And I've been building it with NVIDIA QUANTUM, and I'm using QUANTUM for portfolio optimization work, which is the first thing I'll be doing when I get back, is apart from getting the language model loaded up, is get the portfolio, the simulator working. So this means that we can help you with an algorithm, and then we can help you have it implemented actually on quantum hardware. So you don't have to buy the quantum hardware. You can try and see whether it's something that would fit with what you want to do. So it's like an entry point at a very, very good value. And we're using existing H100s, V100s. I actually use a GV100, and I'm using an RTX A6000. But H100, it's all the same CUDA libraries underneath, works a charm. But I'm using Qiskit, the IBM Qiskit libraries, which is absolutely excellent, so easy to put together. So this isn't 5 years in the future, it's actually happening now. It's in the labs, it's running, which is pretty damn cool actually. And there you are. There's our partners. So Sakai is the one that's doing all the interesting quantum stuff. That's incredible fun, and you have to look it up all the time and get explained as you go along. Oxford Quantum Circuits, which you've probably all heard of. That's all out of the United Kingdom. That's cold quantum computers, and they've got a decent number of qubits now, so you can start doing some more adventurous algorithms. And obviously NVIDIA, who's with us today, hello, Supermicro and 6TeRa. So we've got our own data center as well, a dedicated one for center of excellence, and obviously we've got all over the world. So there you go. That's a little potted guide into what we're converging stuff together, and I just hope there's a few minutes left. If anyone wants to ask any questions now or after, please do. Well, thank you.